In this video, I want to do a related rates problem for you, but before I do that, I want to cover a couple of basics. For example, what is a related rates problem, and also how to identify one. I was a student that was notoriously good at the procedural calculus. I knew how to take derivatives of everything, but I was terrible at being able to identify what type of problem I was encountering and how to apply the calculus to solve it. So related rates problems are problems in which the goal is to calculate an unknown rate of change in terms of other rates of change that are known. And the way we can recognize related rates problems is we'll be given the rate of one quantity that's changing, and we'll be asked to find the rate of something else that's changing as a result. And the example I gave you was that of a spherical balloon. And I said that the air is being pumped into the spherical balloon at a rate of 5 centimeters cubed per minute. And what we wanted to do is we wanted to determine the rate at which the radius of the balloon is increasing at a specific point in time. And that point in time was when the diameter of the balloon is 20 centimeters. Now, hopefully you were able to recognize this as a related rates problem because we were given one quantity that's changing, and that was the volume. The volume was changing at a certain rate, and we were given that. And we were asked to find the rate of something else, and that something else was the rate at which the radius was changing. All right, so that's how we recognize that it's a related rates problem. All right, so let's go ahead and try to solve this problem. And we're going to use the steps that I outlined in the lesson. And the first thing is to always draw a picture unless you're given a picture, right? And so we have a spherical balloon, all right? And so I'm going to draw the picture of my spherical balloon. It's not very good, but that's okay. And we're going to label it, right? And so we know that this balloon, and it's actually a 3D balloon, so we can draw, kind of show that it's 3D. And we know that the radius of the balloon is going to be changing at a certain rate. And in fact, we want to find the rate at which the radius is changing. So that needs to be one of my variables, right? R. And then the other variable that we are working with is going to be the volume of that sphere, right? It says that the air is being pumped into the spherical balloon at a rate of 5 centimeters cubed per minute. And the reason I knew that was volume is because we have a cubic measure up here, and a cubic measure always represents volume. So I knew the volume was changing. So I have labeled my picture. I've drawn and labeled my picture. One thing that I want to warn you about is that students often try to plug numbers in at the beginning, and so they'll label it with a number. So they might, if there was a distance, they might write in the distance that they're given. But you don't want to write anything in, any numbers in that are going to be changing along the way, right? So I'm just going to jump over here and give you another quick example. Suppose you had something where you had a light post and you had a person who was walking away from the light post, and the light post was going to be 20 feet high, and the person is, let's say, 6 feet high. If you're going to draw that picture, you can go ahead and label these with the numbers involved, because we know that the height of the lamp post is never going to change, and the height of the person is never going to change. But anything that is going to vary with time, anything that's going to be changing with time, you want to label as a variable, all right? So that's my words of warning. The next thing you want to do is to write down what you are given and what you are trying to find. So what I typically do is create a little table, and I say, this is what I know, and this is what I'm trying to find. All right, and this takes a little practice because it's not just blatantly given to you. And what we know is that air is being pumped into a spherical balloon at the rate of 5 centimeters cubed per minute. And so how can I write that mathematically? Well, I know that air being pumped into a balloon means the volume is changing, isn't it? It's changing, and I can also identify it as volume because I have centimeters cubed, and centimeters cubed represents volume. So I know the volume of the balloon is changing at the rate of 5 centimeters cubed per minute. And so I can write that mathematically as dV over dt equals 5. right? And it's increasing, and that's why we know it's positive 5. If it said that the air in the balloon is decreasing at a rate of 5 centimeters cubed per minute, then you would put a negative in front of the 5. All right, and do we know anything else? We don't know anything else. What are we trying to find? Well, we're trying to find the rate at which the radius of the balloon is increasing. Okay, so we're trying to find dr over dt. And when are we trying to find it? I always like to put when, because we're trying to find a rate of change at a specific point in time. So I always like to put the when down. And the when here is when the diameter of the balloon is 20. So I could put when d equals 20. However, notice that I'm working with a relationship between volume and radius. So throwing in another variable might confuse things. So if I can change the diameter to radius, that would help us. So we know that when the diameter is 20, the radius is actually going to be 10, isn't it? And so I'm just going to get rid of this and use when r is 10. So we want to find out dr over dt when r is 10. Okay, so the next step is to develop an equation to express the relationship between the quantity you're after and the quantity you are given. And this is the hardest part for students, I think, figuring out which equation is used to express the relationship between the quantities that you're given. Sometimes it'll be 2 quantities that are given, sometimes it'll be 3 quantities that you're given, but you're trying to find a relationship between those. And for the most part, those relationships are either going to be geometric in nature, so it's going to be like a volume formula or an area formula or something like that. They may involve trigonometric identities. They may involve the Pythagorean theorem. They may involve similar triangles. All right, so those are our typical relationships. All right, so and I put those within the lesson. So in this case, we want to find the relationship between the volume and the radius of a sphere. And this is actually geometric in nature. And if you look up the volume of a sphere online, what you will find is that volume equals 4/3 pi r cubed. That is our relationship between the volume of a sphere and the radius of a sphere. So the next step is to take the derivative of both sides of the equation with respect to time. And basically what we're doing here is we're using implicit differentiation, and instead of taking the derivative of everything with respect to x, remember when we did that implicitly and we had to take the derivative of y with respect to x, so we put dy over dx after every y variable that we took the derivative of? Well, we're doing that now with everything with respect to time. So the derivative of v is just 1, and we put dv over dt, and that's equal to, now 4/3 pi is just a constant, so I can pull that out front, and then I take the derivative of r cubed, and that's just 3r squared dr over dt. So we can simplify this, and we get dv over dt equals 4/3 times 3 is just going to be 4, and we get pi r squared dr over dt. Now, the next step is to substitute the given information and solve for the variable you are trying to find. So let's remind ourselves which variable we're trying to find. We're trying to find dr over dt. So typically what I do is I circle that or put a square around it so I know what I'm trying to solve for. And hopefully all of the other variables, we have something to plug in for them. So we know that dv over dt is 5, so I can substitute that in. 5 equals 4 pi, and we want to find dr over dt when r is 10. So I can plug 10 in for r, and of course we still have dr over dt. So now I'm going to simplify, and what I get is 5 equals 4 pi times 10 squared, and 10 squared is 100, so I get 400 pi dr over dt. So now I'm going to divide both sides by 400 pi. So I get dr over dt equals 5 divided by 400 pi. And that's the rate at which the radius is changing when the radius is 10. Okay, and we could simplify that. We could plug that into our calculator and get a decimal for that if we wanted to. The last step is to answer the question. And what we mean by answer the question is you want to make sure you're using the proper units. And in this case, we're talking about the rate at which the radius is changing. And we were dealing with centimeters. So we need to put centimeters per second. Actually, I'm glad that I made that mistake. It's actually centimeters per minute, isn't it? So that is my answer. And again, you could calculate this and get the decimal approximation for that, and that would be the answer to your problem.